Hi everyone, thanks for attending our video presentation. My name is Voisine, VE9REX, and I'll be one of many speakers today talking about Violet, CubeSat NB's student CubeSat for space weather and amateur radio. So CubeSat NB is a team made up of the New Brunswick Community College in St. John, the University of Moncton, and the University of New Brunswick. And since its inception in 2018, we've had about 150 people pass through our team. And this team was inspired by the Canadian CubeSat project, which is a project run by the Canadian Space Agency, with the end goal of furthering space research in universities around Canada. And it does this by allowing these institutions the opportunity of building their very own CubeSat from design to flight. So CubeSat NB has heavily aided in student training in the space sector, and we've encouraged every single one of our students to pursue an amateur radio operator's license. And we're currently in the assembly, integration, and testing phase. This mostly means that we're working a lot on our FlatSat and development and manufacturing of our engineering models before we ship them for test for our flight models. Our current tentative launch date is in summer 2022, and we're going to be deployed from the ISS by the NanoRacks CubeSat deployer. So what is a CubeSat, though? Well, a CubeSat is just a small satellite. It's measured in terms of 10 by 10 by 10 centimeter units. And Violet, which is aptly named after New Brunswick's national or provincial flower, is the name of our 2U CubeSat. That is 10 by 10 by 20 centimeters. And it carries two primary missions, the GNSS receiver for ionospheric and position studies, or GRIPS, and the Spectral Airglow Structure Imager, or SASI for short. So these two instruments will be making observations of phenomena that are linked to the electron content of the ionosphere. GRIPS will be observing radio signals whose propagation velocity is related directly to the electron content, and SASI will be taking images of the oxygen redline airglow at approximately 240 kilometers above the Earth's surface, and the brightness of this airglow is modulated by the electron concentration. So together they provide complementary means to monitor electron content and ionospheric positions. So the redline emission varies heavily with solar activity and geomagnetic and atmospheric phenomena. And the SASI observations paired with the electron density observations being made by GRIPS will allow wave features such as traveling ionospheric disturbances, plasma bubbles, and auroral signatures to be observed. So the GRIPS data will be very complementary to that of the European Space Agency's SWARM mission, and it can also be combined with terrestrial observations in a tomographic analysis. And SASI's observations will also complement observations made by NASA's recent satellite, the ICON satellite. So they have the potential to provide, or SASI itself actually has the potential to provide redline airglow observations poleward of those provided by ICON as well. So GRIPS, generally they want to provide insight into the behavior of Earth's ionosphere by providing real-time position, velocity, and time estimates, as well as the total electron content. And they're doing this by acquiring and recording multiple GNSS constellations available over multiple frequencies. These constellations being GPS, Galileo, GLONASS, and Beidou, and the frequencies being the L1, L2, L5, and L6. And this data will be recorded at an 100 Hz logging rate with approximately 500 megabytes of data per orbit, and we're targeting roughly one orbit of data per day. On the other hand, SASI will be imaging the redline oxygen airflow in the upper atmosphere at the 630 nanometer band using a narrowband filter. And the airglow is very faint. This is 223 photons per second per pixel. And to try and mitigate longer exposure times, we're using something called the telephoto system, which can be seen down here. And further processing of these images will be done on the ground, mostly to reduce blurring in the images due to the length of the exposure times that are required. So generally, this is what our overall satellite design is going to look like from top to bottom in our stack. We have our GNSS antenna at the top, followed by the GRIPS board. Then we have the OBC board right under it. Then we have our UHF VHF board underneath it. Then we have our S-band boards, the SCP and the LNB. In combination make up our S-band boards. Then we have in the center module, we have the SASI controller board, followed by our Z-Torquer board and our PMAC board for magnetic attitude determination. We have our EAOP board, mostly for testing, and then we have our ESIS, IPE, EPS, and battery as well. And finally, in the last section of our satellite, we have the SASI's optical board. So I'll be passing on to Ben Wedemeyer now to take care of the communication side of the satellite. Thank you.
Hi, my name is Ben Wedemeyer. I'm a graduate student with CubeSat New Brunswick. My call sign is VA6RAB. I'm going to be presenting the two radios that we have on board Violet today. So the first radio we have is an S-band radio. We call it the S-band unit, or SBU for short. It's an in-house design radio consisting of three components: the SDR communications platform, a linear microwave board, and the S-band antenna. It uses a transmit and receive frequency of 2.4054 gigahertz. It's a half duplex radio and uses a bandwidth of approximately 2 megahertz. We're hoping for a data rate of greater than 1 megabit per second, and this is because we have a large amount of data to downlink from both the science missions every day. The S-band antennas are another thing we've designed. So they are microstrip dipole antennas that are built on an FR4 substrate that also contains the solar cells. And so they're located in between the solar cells on the solar panels. So we have one antenna per solar panel. One consequence of this is that the surrounding ground planes from the solar cells distort the gain pattern of the antenna slightly. But we're hoping for a close to omnidirectional gain pattern, and this is really because we have a very passive approach to attitude with just the permanent magnet. And so this means that we really need to be able to communicate in many orientations. The properties of the antenna are that it has a Saturn frequency of 2.4205 gigahertz and a bandwidth of approximately 35 megahertz. We're also using a balun that is a 1.5 to 1 turns ratio balun, and this is for impedance matching and conversion between unbalanced and balanced signals. The second radio that we have on board is a combination UHF-VHF radio. We're calling the VUB. And this is an off-the-shelf radio purchased from EasySpace. The model name is a TRX-VU, and it's a full duplex transceiver. It also has an FM transponder mode. It also has the capability of downlinking telemetry, receiving telecommands, and beacon capabilities. Part of the reason we have this radio is because we are required to receive transmit shutdown commands in the case of a rogue radio. It uses a transmit bandwidth, a transmit frequency of 436.830 megahertz and a receive frequency of 145.910 megahertz. And this also allows us to gather system status and downlink telemetry while the S-band unit is downlinking data, so kind of allowing us to really use our passes really efficiently. And because it's a UHF-VHF radio, we do require two antennas. These two antennas are provided by a deployable VHF-UHF antenna that we built in-house. So obviously two antennas, one for each frequency. They're monopole antennas, and the antennas are stowed in behind the solar panels during transit. They also contain an RF matching network required to match the impedances of the antenna to the VUB, and a simple nichrome wire burn circuit is used to keep the antennas in place while the satellite is in transit to orbit. I'm going to pass it off to the next presenter. Thank you very much.
With regards to the software on the satellite, the target platform for the onboard computer software is CSP running with FreeRTOS. FreeRTOS is a real-time operating system kernel for embedded devices, which will support the satellite's submodules and provide memory management, semaphore timers, and more. CSP is the CubeSat Space Protocol, a network or transport layer protocol comparable to a connectionless TCP/IP protocol stack. CSP was originally designed by a student from Aalborg University in Denmark and simplifies connectivity between distributed embedded systems. The diagram on the right shows a CSP addressing example. Addresses range from 0 to 31, with the satellite using addresses 0 to 15, and addresses 16 to 31 are for the ground. These are the onboard computer modes. Initially, using the subsystem's feedback, we check if there are any faults detected. If so, we enter the failure mode, then identify the source of the failure and assign the significance or level. If there weren't any failures in the feedback, we would check if there's any maintenance or calibration needed. This would include battery charging, instrument calibration, grips, SASE, and ADCS. If so, we would enter maintenance and calibration mode. If not, we would move on to manual mode. Manual mode should activate by command from the ground station. If everything is okay, it will return to normal mode, which is also known as mission mode, which is where the OBC collects data from payloads, and the scheduler then assigns tasks and defines the current satellite operations. Next, we will briefly cover the design of the second stage bootloader for the OBC. The bootloader is currently being developed and will allow for the verification of a software's image's integrity before loading, providing flexibility to load different versions of the software when desired, including uploading new software from the ground station for the OBC to run. Quickly looking at the flowchart, we can see that the STM will contain flash memory, which we will call the internal flash memory, and outside the STM, but still on the OBC, we have another flash memory which we will determine as the external flash memory. The internal flash memory is structured into 3 sections: the boot code, the gold copy, and the silver copy. The silver copy will be used as default, and the gold copy exists for backup for when the silver copy fails. For example, if there was a power outage while loading the silver copy, then we could potentially revert to the gold copy. The satellite software is being written using the C programming language. Additionally, software being developed will follow the Power of 10, which contains rules for developing safety-critical code by NASA. This includes rules such as not using dynamic memory allocation after initialization, and attempting to limit the size of functions to about 60 lines of code. To verify the software independently from the hardware, a custom simulation framework was written to simulate the EPS, CAN bus communications, and the ground link communications, allowing for rapid software development without needing the hardware.
Violet has 3 amateur modes, which are meant to be used by anyone with an amateur radio license. The first of these modes is Packet. We've chosen to go with 1200 baud AX25 due to its compatibility with a wide range of hardware and software. This will use the VHF and UHF radios on board Violet. Opening an AX25 connection with the satellite will provide access to its Bulletin Board System, or BBS. A BBS allows users to write posts and replies to posts, which are viewable to anyone who connects to the BBS. They are quite similar to internet forums, except that they are accessed via a text interface instead of with a web browser. Traditionally, BBSs could also be used for a variety of things, such as downloading and uploading files. We've chosen not to implement this due to the amount of storage space that would be required, as well as the limited bandwidth available over VHF and UHF. Posts will be stored in non-volatile memory, and newer posts will overwrite older posts to limit the amount of storage space required. We plan to limit posts to around 1,000 characters, and allow for a few hundred posts to exist in the system before overwriting old ones. The next mode offered by Violet is the FM transponder. This also uses the VHF and UHF radios on Violet. Essentially, anything that breaks the squelch on the uplink frequency is transmitted in real time on the downlink frequency. This allows Violet to be used as a repeater. Since Violet isn't doing any processing on the audio, it's a very flexible mode, allowing for voice, packet, SSTV, or anything else that can be used over FM. It's also very simple for operators to use, as it only requires a radio that can transceive on VHF and UHF, as well as an accompanying antenna. The final mode is S-band record and playback. In 15-second intervals, Violet will switch between recording on the S-band receiver and playing that recording back via the S-band transmitter. The reason for having 15-second intervals is to allow contacts to be made over FT8. FT8 is a low-power, low-bandwidth protocol which is primarily used for making contacts. Allowing FT8 to be used on S-band makes it possible for the operator to use cheaper and more accessible equipment. Traditionally, S-band is a more difficult band for the average amateur radio operator to access, often due to hardware costs, so lowering this barrier to entry should make the S-band mode more popular. Of course, the S-band mode is quite flexible and can support any other mode of operation. The only requirement is that it fits within the S-band transceiver's bandwidth.
I'm Brent, VE9EX. Part of this project is the ground station. Shown here is the removal of an old C-band dish and the preparations of the site. In our ground station we also have an ICOM IC9700, and I had the pleasure of testing that this summer. I had my first 1.2 GHz QSO with Burn VE9BJK. The UNB Amateur Radio Club is also involved in this project, and shown here is a satellite contact event. In conclusion, it's been a fantastic project for student education and training. We thank them all, and we also thank our primary funding from the Canadian Space Agency and the New Brunswick Innovation Foundation. We hope you enjoyed the presentation. Thank you very much.
Hi, welcome everyone to our presentation on the ALEASAT mission. We're very excited and grateful to be presenting to you all at RAC's AGM. But before we start, I'd like to thank our sponsors, particularly MOMENTUS Space, the University of British Columbia, and the Simon Fraser Student Society. We'd also like to thank RAC for partnering with us in this project. We really wouldn't be able to do this without everyone involved, so thank you very much. So just a little bit about myself. My name is Julian Mentasti. My call sign is Victor Echo 7, Uniform Delta Papa, and I'm the old team captain of UBC Orbit. So today what I'm going to be presenting is I'm going to be providing a mission overview, then I'm going to be diving into our imaging payload, our communication system, and then I'm going to be talking about ALEASAT and beyond. So starting off with our mission overview. Nobody here is a stranger to telecommunication networks going down. Usually they go down for all sorts of reasons, whether these are physical events such as natural disasters or even usage. When it comes to physical events, these will usually disable the network. For example, in 2017, Hurricane Maria took down 95% of Puerto Rico's cellular network. But in other cases, when natural disasters don't disable any of the telecommunication infrastructure, but an increased usage in more phone calls on the network, more people trying to use it, this means that there's going to be oversaturated networks and calls end up falling through. People can't reach 911 and communications can't go through when needed. So amateur radio has filled in this gap whenever these events occur. They're able to quickly set up networks and transmit essential information, and they've been great at relieving, at doing disaster relief. And our goal with this project was to provide an additional tool for the amateur radio community. So a little bit of project background. ALEASAT is a collaborative satellite project between SFUSat and UBC Orbit under the supervision of Professor David Michelson. We'd also like to thank the UBC Radio Science Lab and the Simon Fraser University's Aerospace Physiology Lab. And this project began back in January 2020 in response to a unique launch opportunity. At the time, both SFUSat and UBC Orbit were working on satellites for the Canadian Satellite Design Challenge. So when the unique launch opportunity came, we decided to join our satellites and ALEASAT was formed. And ALEASAT has three main mission objectives. The first one is education. We want to provide UBC and SFU students with the opportunity to design, build, and operate a spacecraft. Furthermore, we want to support educational outreach activities for university and secondary school students. Our second mission objective is amateur radio. We want to provide the amateur radio community with a training satellite to assist in disaster mitigation and relief via on-demand satellite imagery, and I'll talk a little bit about this later. Lastly, student research. We want to investigate the performance of different onboard image post-processing algorithms and see how they perform in space. So just a little bit about our image ConOps and how exactly an amateur radio operator will be able to request and receive an image from our satellite. Firstly, what they're going to have to do is register using our online image request portal. Once they've registered, they'll be able to submit image requests. Once they submit an image request and it's been approved, the amateur radio operator will receive a one-time token to identify themselves with the satellite, and the image request portal will send the request to our control center. The control center is going to transmit the image request to the satellite on its next scheduled pass. Once it's sent, it will be scheduled. The satellite will just conduct normal functions until it's time to conduct an image request, in which case it's going to begin pointing to the right direction and use its GPS to synchronize its location to make sure that it's taking a picture of the area that it's supposed to. It will capture the image, and then in the same pass, the amateur radio operator will be able to communicate with the satellite. They'll be able to transmit their one-time token to identify themselves. And once that's completed, the satellite will begin to downlink the image directly to the amateur radio operator. The image is going to continue being stored on the satellite until its next scheduled pass with the ground station. In which case the satellite is going to transmit the full resolution image to the ground segment. And I'll talk a little bit more about this and what it'll look like. So just to give some information on the ALEASAT spacecraft itself. ALEASAT is a 1U CubeSat. A CubeSat is just a standard for miniature satellites, and a 1U, it is just a standard for the size. It's approximately a 10 by 10 by 10 centimeter cube. So if you have a 2U, that would be a rectangle, two of those cubes stacked together. But we're a 1U CubeSat, and as you can see from the image on the right, we're just a cube. Our launch is being arranged by MOMENTUS Space. It's going to be done on board a SpaceX Falcon 9 rocket carrying the MOMENTUS Vigoride transfer vehicle. And this transfer vehicle is going to deploy us to our final orbit, and we're targeting a 500-kilometer altitude on a sun-synchronous orbit. So now, let's dive a little bit deeper into what this image will actually look like. Well, firstly, it's going to be taken by an R2CAM sensor. It's going to be 5 megapixels, and it's going to have a pixel size of 1.4 micrometers. It's going to have a Bokoptronics lens with a focal length of 35 millimeters and an aperture of f/7. We're expecting to have a field of view of 52 by 39 kilometers at 500 kilometers. And as you can see from the picture on the right, if we were to center an image with this field of view over the Greater Vancouver area, this is what it would capture to provide some context. It's going to have an effective resolving power of 90 meters per pixel, and we have a target exposure value of 15.6. To provide a little bit of context on this exposure value, we have two images taken here from other satellites with a slightly higher exposure values, but we're expecting to get a value somewhere similar to these. Now, just diving a little bit into our image compression, we're not able to transmit full resolution images to the amateur radio operators, and I'll talk a little bit more about our communications later, but we begin with a 5 megapixel image that is 6 megabytes in size. We're going to apply some pixel binning, lowering it to a 1.25 megapixel image. And then we're going to apply some post-compression and post-processing to lower the size even more. It's still going to be a 1.25 megapixel image, but the final data size is going to be 154 kilobytes. And this should be enough to transmit to an amateur radio operator on a single pass. And just to make sure that we're taking a picture of what we actually should be taking a picture of, we're going to be using active control using 3 magnet torquers so we can properly point at what we're supposed to be pointing at. Our attitude determination is going to be done using sun sensors, gyroscopes, and accelerometers, just so we know where we're looking at. And our positioning is going to be done using a GPS receiver. The video on the right shows our control system, and it's using a placeholder satellite model. Our satellite doesn't have deployable solar panels, it's just a cube. So now once we have an image, we have to transmit it to the amateur radio operator or the ground station. And in general, we have a half duplex connection, and both our uplink and downlink is going to be using the 70 centimeter amateur satellite service band. On our space segment, our satellite is going to have redundant V-dipole antennas based on an in-house design. And our ground segment is going to have a circular polarized Yagi from M2 Antenna Systems. Our ground segment is composed of this. We're going to have a single ground station antenna, as you can see from the image, located at the UBC Vancouver campus. But we're going to have 2 control centers, one at the UBC Vancouver campus and a remote control center at the SFU Burnaby campus. Both control centers will be able to do the full operations, send commands, and collect telemetry from the satellite. Our uplink is going to be encrypted, but our downlink is going to be unencrypted. And currently, we're exploring potential telemetry downlink to the SatNOC networks. Our ground segment is based on the Canadian Space Agency's amateur ground station, and it's going to be using a USRP TXRX using GNU radio for telemetry DSP. We're going to use a circulator as a TXRX switch, and we're going to have a Yagi antenna. And our maximum PA transmitting power is going to be 17 decibels. Just to dive a little bit into how often and how long we can communicate with the satellite, at 600 kilometers, we're expecting to communicate with the satellite 4 times a day, and each pass is going to be roughly 400 seconds. At a lower altitude of 400 kilometers, we expect this number to be 3 passes per day and around 300 seconds per pass. Our target altitude is 500 kilometers, so we expect the numbers to be somewhere in between there. And as our satellite stays in space, it'll slowly start deorbiting, and we expect both the number of passes and the pass duration to be lower. And we're using two different communication protocols to communicate with a satellite during these passes. Whenever we're communicating with an ARO, we're going to be using AX25 digital mode packet radio at a 9600 baud data rate. This will allow us to transmit roughly 1 image per pass, and it'll take us less than 150 seconds to transmit an image. Whenever we're transmitting to our ground station, we're going to be using the CC1110 protocol at a much higher data rate of 20 kilobits per second. And this will allow us to transmit 3 images per pass at a little bit less than 70 seconds to transmit an image. So once we have an image and we're able to transmit it, what are we actually going to do with it? Well, this is what we hope to do with ALEASAT and beyond. Firstly, what we want to do with this is have an amateur radio training program. In the short term, we want to connect amateur radio operators involved in disaster relief and provide them with the satellite and provide them with the skills needed to take photographs using ALEASAT. We also want to provide some training into system response times so they're able to schedule this properly. In the long term, we want to equip the amateur radio operator community with the skills needed to take advantage of a more permanent disaster monitoring constellation mission. And the way that we're hoping to do this is through a mix of online modules and live scenario-based exercises to truly solidify these skills. And what we're doing isn't new. Back in 1996, UOSat 12 provided satellite imagery directly to amateur radio operators as part of the initial disaster monitoring constellation. But then over time, a disaster monitoring constellation started waning away from using amateur service bands. What we hope to do with ALEASAT is bring back amateur radio into the disaster monitoring constellation fold and provide this very useful tool. So they're able to use remote sensing imagery whenever they're dealing with disaster situations. The landscape is always changing, and sometimes having a bird's eye will be able to provide a lot of information. So what we want to do is help train amateur radio operators, and we also want to act as a proof of concept for future more complex constellation. And so thank you very much for watching our presentation, and we're looking forward to answering your questions. Thanks.